Take it away.
Okay, so Unity seems to be pretty popular these days, and we're getting a lot of people doing 3D games, but I'm a big fan of 2D games. I'm like, how can I rig this thing to do 2D? So I've thrown through a few examples of different ways to achieve 2D graphics in Unity. Do many people in this room use Unity? Much? Yeah, a few people? Okay. So I might be wrong on a few things, but I've done a few experiments. So basically this first resolution is shocking. So this first technique basically uses the Unity editor to set out planes, and then each of the plane has its own basically texture, XY position. So putting up some sprite sheet. And when I lay them out in the editor, I just have a snapping script that snaps it to a grid that I define. The handy thing about this is it's very easy to use. You can see it while you're working on it. And you're able to apply physics to certain things. So, for example, these barrels just have rigid bodies on them, and it allows me to handle some collision. Very simple stuff in this one. It's all on one layer. Ideally, if you were doing up a map, you'd want it to have a few different layers. You'd want to show what is underneath the player on like a ground layer. You'd want to show what's on the same layer as the player, so you get the proper type of depth thing. Whereas here, those barrels are on the bottom layer. So yeah, basically, this one's very flat, but you would want to do things that are above, in line, and below. And it's very simple to do this kind of thing. Again, the resolution is very zoomed in. But basically, you're adjusting the UVs based on which tile you want to use in a sprite sheet. A few formulas here specifying each UV in each quad, and it seems to work pretty well. You'll see got a bunch of errors here, and this is just because Unity doesn't like you using different UV sets in the editor for the same mesh. There's probably a way around it. I've been playing around with this for about a week, and I'm not really sure. I haven't come across a solution, but it doesn't seem to have any actual effect on the game once you're running it. It's just purely in the editor. Okay. So there's another way to do something very similar, whereas you can access OpenGL immediate mode through Unity to draw directly in screen space, which is pretty handy, which is how I've done all my general 2D games. Oh, another note with the, sorry, go back to the other one. It's important to have on your camera, you want to have an orthographic projection. It defaults to perspective, which basically what that means is when we're in perspective, your view frustum is a prism. So when you're mapping to the screen, it all basically gets squished, and that's why you get the foreshortening in the distance. The orthographic is more of just a cube, so it maps directly, and that's exactly what you want for 2D like this. You just want it straight projected onto the screen. So back with the GL. Okay. So if you've used OpenGL before, this is probably pretty similar to what you've seen before. If you're not applying any matrices in your shaders, then you are pretty much just drawing in screen space. Something that I didn't expect to come across, but it seems pretty obvious now that I've actually written it, is that because Unity is having any resolution at once, you have to sort of map to it. So I've got these world sort of positions where I imagine maybe it's 400 by 400, it's a square or something like that, or maybe it's not a square. But the way that it maps it is between 0 and 1. So you need to normalize it to a range like that. And this is what this function basically does, and it keeps it square. The first ones I was doing, they were a bit rectangular. Because they were pretty similar ratios, you maybe didn't notice it as much, but it was something that did need to be fixed. Again, if you want to map textures and stuff, but you're going to have to pass UVs through to a shader and write your own shader. You can use GLSL or CG, basically. It all gets wrapped in a Unity shader, which they're a little bit different to writing it normally, but...
Is that GL an emulation layer, is it, or is it really OpenGL called?
Depends on what you're running it on. Because I think on Windows it wraps DirectX, but on Mac it just uses StratGL. So I assume it is StratGL. It might be their own flavour a little bit, so it might wrap a few things. But
does that mean you're using the paid version of Unity?
No, up until about a week ago, I was just going to say, oh, you can use this, but you need the paid version, the pro version to do it. But I'm like, oh, I'll have a look just to make sure, and it seems to be in the free version, which is strange because I swear, like 3 months ago, I went to use it in Unity and I couldn't do it. So maybe it's something that changed recently.
Are you using 4?
No, this is still free. I haven't updated it. So yeah, it's odd, but it's I'm a big fan of drawing in screen space for 2D graphics.
When you do that, do you get pixel perfect textures so they map 1 to 1?
Yes, it should. It's just the same as you would writing it in OpenGL, basically. So, yeah. It's still mapping a texture to a quad. So if you zoomed in heaps, it won't be pixel perfect. If you zoomed out heaps, it won't be pixel perfect, but it's mapped to a quad. Okay, this next one has, we're moving into a bit more 3D stuff now, but implementing some 2D techniques in a 3D space. So in here there's 2 types. We've got the heads-up display, so you've got a GUI type thing. And the way that is handled is on a separate camera, which is just pushed off to the side. Again, orthographic projection. So like I was saying before, how it's more of a rectangle for the orthographic. The perspective is like a prism. So again, that prism gets skewed into the screen space.
I haven't used Unity much. Do you have support for having, like when you say off to the side, so they're in the same space, can you actually have a totally separate space? Because I'm just thinking if somebody fires a cannon or something like that and a cannonball happens to go through your HUD camera, are you going to see it go through your HUD?
Probably. It seems to be you have one scene and that's how it handles everything. So
Unity's funny like that.
yeah, I think you're kind of stuck, and that's a good reason to use GL calls because it's not in your scene and you draw it when you want. And you're not using a camera.
I think you might be able to use layers to separate them out.
Yeah, well, we have got a layer thing here. I'm not sure if that's a rendering layer or if it's a physics layer or something.
I think you can apply it to both.
Turn off depth testing for that.
Yeah. So if you want to do this type of camera, set an orthographic projection, move it off to the side somewhere. That's all it is. It's a Unity plane, and they use so many verts for their Unity planes.
High detail.
Yeah, they want to add terrain to it or something. I'm not really sure. So with the camera though, to make sure you want to render the environment behind it, you also need to set clear flags to depth, and that's how you set it up, basically.
Have you tried implementing OnGUI in your...
I'm really not a fan of the OnGUI stuff that they've...
UI in Unity is terrible, so let's get that out of the way. But if you don't want to have another camera, just you use the OnGUI, and there's all these GUI functions to render text boxes and labels.
And textures and that kind of thing.
And you can skin it, but it's really awkward to use and hard to set up skins and stuff like that.
Yeah.
Wasn't it the catch with the OnGUI is actually called several times per update, wasn't it?
I'm not sure.
I think it was.
It's a weird system for doing UI.
The good thing about having it actually done here is you've still got access to all your transforms really simple. And it's not a bad way of doing it. So also in this scene, we have, there's a few names from there, generally billboard sprites is how I've known them. So a few of these are camera-facing sprites, and the blue ones aren't. So they'll always be facing the camera. And we used it on our graduate game with these exact graphics for our pickups. Our concept artists did all this great work for these pickups, and I thought, I don't think we'll really get the same effect we want if we model 3D assets for it. So let's just put these in, let's have them as camera-facing sprites and call it a day, basically. So in order to get these ones, it's not as simple as just putting a lookup command towards the camera, because then you get, if it's straight in front of the camera, it's perfectly fine. If it's to the sides, things will look a little strange. So what you want to do is you want to look at a position that is along the camera's facing direction. So you're looking at the front of the camera, and that will allow it to perspective correctness, basically. And there's the formula for it. Now, if we want to move into more of, I guess, a more advanced 2D animation in 3D, this character here is drawn up in Flash, then turned into a texture in Photoshop, and then rigged in Maya and animated in Maya, and then brought into Unity to use it. It seems like a long path, but there are quite a few advantages to it. So what it actually is we've got several different planes. And each of them we can map a different graphic to it. So I could change what his arms look like, his head looks like. And then the reason I took it into Maya to animate it is that I've got this 3D rig now. So I can play around with curves, IK chains, that kind of thing. And it's really quite cool. And another advantage to it is sort of dynamic post-animation animations. That probably doesn't make much sense. But because I've got a rig there, I can animate things like his head. I can just move his head joint and things like that. I can adjust it in code later to do what I want. And yeah, so it's a pretty cool way to do it. I originally had a perspective projection on this, and it looked kind of cool. You could have 3D walls and stuff like that, geometry around him. The problem you get with that is when he moves to the side, there is sort of perspective, and you tend to get gaps between the joints, or things will not quite be right. So it's probably a good idea to stick with the orthographic projection. I had slides with notes, but I haven't looked at them once. So just make sure I haven't missed.
We've only got a minute and a half left.
And still a couple of techniques to go.
Yeah. Okay. So now the next ones are not necessarily 2D graphics, but they're a form of non-photorealistic rendering. So toon shading or shell shading, if you will. On the right here, we have a simple diffuse shader. All of these come with Unity, so I haven't done anything special here. The second one is their flat shaded toon shader. It takes no light. It basically gets the exact texture, puts it on the polygon, and then it draws an outline. And then the last one is a shaded one, so it has solid shaded lines. A good way to handle these is, usually you won't have as much detail in the texture, you'll have a simple colour or something like that. So if I turn off the texture, you'll see we've got these hard shadows, there's no in between. It's either dark or it's lit. And the way that this shader handles the outlines is, first it draws just the plain shaded, basically, so we've got the white, the shadow, all that kind of thing, and then for the outline, what it does is it expands the mesh based on its normals, so it gets a bit thicker, and then it only renders back-facing polygons. So you end up getting a nice outline. So sorry, it'll go the other way. You render the outline and then you render the art over it, basically. And now we'll move quickly down to the last one, and this is a different...
You are actually out of time now.
Out of time?
Yeah, give it a minute longer.
Okay.
Just
So, with this one, basically it takes the normal compared to the camera to figure out whether it's an outline, and then it also adjusts with the lighting. So you end up getting these inky, thick lines in certain places. Yeah, so that's my toon shading type thing. Any questions on any of those?
Anyways, after you've done this investigation, would you continue using it? Because you've done the Marmalade before this, and then...
Well, originally when I did a few of these, I was looking at doing a 2D game, and I was going to use Unity because that's what we used at uni, and I was kind of familiar with it. But I ended up running into new problems, and I thought, oh, I'll go write my own engine, and that's not a quick thing to do. But yeah, going through all this, I mean, the real key that you've got in Unity is you've got this amazing editor that just I wouldn't be able to build by myself. So it definitely has its advantages. If you don't want to write your own engine or graphics libraries or anything like that, it's pretty good. You won't get as good a quality thing as if you write it yourself, but it's all there. I mean, I threw these together sitting on the train going home from work. So
what's the pro version of Unity worth in Australia?
You guys probably answer that better than me.
Yeah, so it's 1,500, was it 3,000?
No, it's about $1,000.
Yeah, it's
Plus you add on
yeah,
for other platforms.
500 for the Pro, but then if you want to deploy it to iOS or Android, you have to get another plugin for them. $1,500 each as well or something. So if you just use the free one and want to deploy to Android and iOS at $400 for each one of them.
You're probably going to spend $2 to $3 if you want the full package. But you can the base PC thing for I think it's for Mac and Linux as well is about $1,000 to $1,500 something like that.
Should also note this is the free version, so anything here has been completely free, and I don't think I wrote much code for this. I wrote sort of the GL and the planes and the editor stuff, and the builder stuff, but the shaders, they just either came with Unity or I found them online. There's a lot of stuff out there.
Are they regular Unity shaders?
These ones come with Unity. This one I copied off the internet.
Because if you need to mess around with those ones that come with Unity, you can actually download the package of all the built-in shaders, and so then you can edit them and do stuff with them.
Since we've done a small game using Unity as well, we found it's like easier to just write sort of a bit of helper code, so you can do common sort of things like a sprite cutter. So since you have your sprite sheet and just reference it by naming the code instead of having to have a separate object to cut it out each time.
The way that I handled the sprite sheet in this first one is I specify how many graphics are along the width and how many along the height, and then I can basically map coordinates depending on which cell you actually want. So they're rectangular cells depending on the height and width, but it's could all be all you need. I mean, how we doing, Ash?
That's about it. Who wants to go next? Cool.
Shall I use your computer there, or what you want to do, or whatever you want to do? Yeah, if you want to use the button, yeah, that's fine.
This isn't needed.
Yeah, I think it might as well since it's out. Oh, it's going to be the other way around.
Yep,
Oh, the
sheet
sheet
is that way.
the Windows. What's the button there? Oh, it's not all that fast. It's probably not marketing it.
Who wants to? That's right.
Yeah, I'm just
worry about
yeah, it's just easy, even artists pick it up and they can just throw something together.
yes, so
We've used it just to display models.
going after a version anyway. He just had a model running through an environment he set up, and that was it.
Yeah, exactly. That's what it's perfect for. And then,
Oh, and a math, okay.
it also lets people do 3D. Like I suppose if you get Flash or something, you play with 2D graphics, but to do 3D is probably the easiest one to pick up.
I actually made the mistake of over-engineering it when I was first getting into it. Because I was coming from a C++ background, so I was working on this 2D platform, and I'm like, oh yeah, I'll do all the collision in code. But Unity has its own 3D collision system, and I should have just used that.
Yeah.
Collision was so broken. It was for a week long game contest though, so things were pretty rushed.
So what you're saying is you probably shouldn't have wrote your own physics engine in the week-long game contest.
Yeah. It was 2D, so, you know, I'm like, oh yeah, I can do that.
There's a called like a physics engine 2D called Fastia, which is quite in Unity. Played that one at all?
I haven't heard of it.
Has anyone heard of Futile? It's supposed to be quite good. It's a 2D, open source 2D kind of layout on top of Unity.
The 2D toolkit for Unity is actually pretty good. Work with that. Not sure how the licensing works, but a friend of mine has a license for it. I think it's free, and it's basically a whole package for handling animation, sprites, textures, and it's all stuff you can do in Unity by yourself. But
I like writing my own stuff.
yeah,
Right.
which is what
There you go.
Yeah, I might go fairly quickly.
Yep.
So constructive solid geometry, the basic idea of it is to make complex shapes out of simple shapes using a few simple operations, add, subtract, and something else I never really cared about. And the motivation for this was some years ago I was tasked to make a procedural architectural features for a virtual home project, and learned lots about stairs and balustrades and things, all about buildings that I ever want to know. Since forgotten. So this is the test bed that you used to try and make. It's not quite as I remember it, but it does seem to run. Please do run. Don't tweet this in.
Is it running in like DirectX 3 or something, is it? How ancient?
Yeah, it's actually DirectX 9, I believe, or 8. I think it's 8. Yeah.
I did a training video on.
Oh, it did it here. There we go. It's a good thing to move this guy a bit closer. See what it actually is.
Have you got sprint kit?
I do. It'll probably go very fast. So what we have there is a control these things. So what we have is a cutter object moving inside a, we're subtracting the red object from the other object. And we're just recreating the thing every single frame to show the result. You can find the insert key here, that sort of stuff. And we can take a stab at it, we can just make it final there. Change our cutter object to a circle.
I'm watching the frame rate drop
Yes,
from 800 down to 8.
Well,
yeah.
the funny thing is that the original version of this, I wanted to show this because it's kind of cool, was to make some drill noises and go zzz, and actually drill through it in real time, but it clearly doesn't do that anymore. It did at some point in history do that. So, try and tell it that now that we've done that, we can steer the camera around and look, we've subtracted stuff there, we've kept some smoothing groups there. And so you can just keep cutting away with your objects to make things like that. Okay, so how do we do this? Yeah, so if you look up CSG in a textbook or online, you'll often find people talking about using fancy data structures to do this, and they often say use a BSP tree. Some others use winged edge structures. The main point is that they're trying to keep watertight models, they're trying to maintain a specific structure so they can do these fancy add and subtract operations. But in the real world, like a game studio or anything else, you end up with polygon soups, full of degeneracies, all sorts of rubbish really, and certainly not watertight. And so I mulled over it for a bit and thought maybe there's a simple way to do it with just some basic geometry options, and came with this algorithm. I haven't seen anyone else do it, but I'm sure it's done many times because it's so jolly simple. So rather than go through that, this is a pictorial. Imagine that the two objects are two-dimensional, and we're going to subtract B from A. All we do first is we flip the faces of B inside out so we can have caps. Then we split all the faces of B by the planes of A. We just do, does this triangle or does this polygon intersect? If they do, use the plane and cut it. So cut it there. Then we want to get rid of all the bits that aren't important to us. So we say, is the face of B, can it see the back face of A? You can see there's some like raycast type tests there, or just the visibility tests, looking from the faces. And the ones inside we can see, the ones outside we can't see. So we just don't keep them, and we're up to that stage. Next thing what we do is we grab the faces of A, we do an intersection test with all the faces of B. Once again, if they intersect, we cut them by the plane. And then, this is where we have a bit of fuzziness, because our models aren't convex, nor are they watertight. We just cast a few rays out again. In this case, we can do it as simple as in each of 6 directions on the axis. Because the polygon's already cut, nothing spans. It's all either inside or out. From the centre point of the polygon, if we can see a back face of B, then just remove it, otherwise we keep it. End result is that. So it's not, oh yeah, if you want to do an add operation, it depends how much you care. You can just keep all of A and B, or you can try and remove internal faces, and the principle's really the same. You're trying to cut up your model, just intersect your polygons, split them into more pieces, and then try to find am I inside or outside the space. If you have convexity, you can do a test there. Otherwise, you're just going to look for back faces, and the idea is if I can see back faces, I'm probably inside. Iteratively remove stuff until it's gone. So this is some of the results from that. Actually, don't go too far. I did go too fast on now.
Actually, Greg, do you know about, just with you saying if you can see back faces, do you know about the odd-even rule? Would the odd-even rule work for that?
Odd-even rule.
You might know, okay. That's the thing with, so like trying to do polyfills on non-convex shapes where from one point, the number of times you cross a plane, whether that's odd or even tells you whether or not
Like
you're
Jordan
inside or outside the
curve
space. Sorry,
Jordan curve
Yeah.
theorem.
I'm not sure. Yeah.
The simple.
It is possible. If you traced a ray, you might say, yes, I'm entering, I'm inside. You might be able to use that logic.
I think it would be if you cast a ray and you get number of back faces and number of front faces you hit, and whether that number turns out to be odd or even, I think it would tell you whether or not you're inside or not.
Yeah, no, it makes sense. It's a common way for 2D polygon intersections. Required tools, not much. If you're handy with a dot product and your vector 3 and your matrix maths, or a library that come with anything, Unity or DirectX or whatever, you can do that. Intersecting polygons, ray with polygon, plane and polygon, so what you'll find online or you can write yourself in a few functions. To actually make it practical, you want to have a few other things. Extrusion, you want to get a 2D shape, just take a 2D contour and extrude it into useful shapes, tubes or open tubes. Texture coordinate generation, to make something look good, you want to just use, like in any modelling program, cube, sphere, planar mapping. Mesh processing, you're going to want to decrapify it, remove T-junctions, remove point and lines, that sort of stuff that doesn't give you good results. And you want to keep smoothing groups so that you can keep nice normals as you're working with models. You will encounter the usual suspects, floating point precision problems. You're going to use epsilons. The trick with epsilons is you want to use them in the right places, and you want to use the same code for the same test. If you have a visibility test or a test, you want to make sure you're exceeding exactly the same function. In this case, using standard 32-bit floats and using fairly fat epsilons. triangulation. If we keep to simple triangles and polygons, it's not too bad. If you go complex, then it's actually a very non-trivial thing to work with. I don't have a picture of one, but I can show you how once a polygon sort of degenerates into a point, what actually might happen is if it passes that point, it actually becomes a very complex polygon with re-entry. Most of those 20 lines of code versions do not work. Performance, if you're going to do it in real time like we're attempting there, it's pretty slow. You want to throw your points into whatever you can, 3D hashes, grids, arteries. The problem is that your data is dynamic, so you can't build a beautiful structure. You're going to work with something that's a compromise, but you can still get some acceleration out of that. That is it. So there's some results from the test bed building, some roof there, those just using cutting planes and so forth, and extrusions. There you go.
Very cool.
Any questions there, folks?
Did you stick with triangle mesh poly soups, or did you sort of, because I was just thinking about, you talking about cutting on your planes, you'd probably get better results, I imagine, if you started with end polys, if that makes sense, so quads and up.
Triangulate.
And then split them first and then only make triangles after. Did you just go, but I imagine the code's probably a lot simpler if you just go with triangles.
Yeah, the little thing I made there, I made a class called winding, which is n-gons. So
Right.
yes, it can be more than 3, and then you can triangulate, so you can say, turn myself into triangles, and just provided, cut with the plane and a few little helpers there. So basically for this, made a polygon class and a little CSG which does subtract with a few variations.
How long ago did you do this?
That was about 2003, I think.
Oh, okay. Yeah. Because have you heard of a library called Carve? Carve, yeah.
No.
It's a freeware library that basically does that. It does the CSG operation.
Right, yeah. I remember looking at the time. In fact, when I found this, I found a few other little experiments nearby which did some 2D stuff and whatever else. And did a trip down memory lane, but yeah, there wasn't much available at the time because I would have liked to have just
Yeah, so if
used it.
anyone else wants to do those sort of things, I've used the library in Carve, it's pretty good.
We'll do real time though.
Well, I haven't sort of stress tested it, so I don't know how fast it is, but
Okay. Thank you.
She's very good.
Who wants to go next?
I'll go for one.
Well,
What do you think?
oh well, yeah, I might as well go. Yeah, sure.
If I can use your laptop, yeah, because I've got the same thing.
Now, what if everyone came with a thumbstick?
Then we'd be in trouble. We'd all be here, thumbstick fencing.
Should we throw something together?
Yeah.
Got some brand there.
We'd find a whiteboard, that's what we did. Go old school.
Okay guys, my talk's a bit more abstract. It's about cellular automata and how they relate to symmetries. So because it's abstract, I think you guys can work out yourself if there's any relevance to games, how it could be incorporated in the game. It's up to you. Right, this is an automaton. 1, 1, 2, 3, 8, 13. It's an automaton because it follows a rule, and the rule is, if we look at this number 1 here, the rule is take it, add it onto its previous number, and that becomes the next number. Right. Yeah, it gives the Fibonacci sequence. And the important thing about this rule, this is time going down this way, is that it's the same rule at every time step. So in terms of symmetry, we can say that it's got time symmetry. So that's an automaton. You could say that it's a cellular automaton, but there's only one cell there. So let's expand this and say that we've got a row of cells, and just to keep it simple, let's say that we're just working with booleans here, on or off. So here's a row of cells, and we can do something similar to this. We come up with a rule. So in this case, the rule is take a cell and add on the 2 neighbouring cells, where black is 1, white is 0, And if the result is odd, then colour in the next cell down. So this is time going down this way, so that's the next time step. So if I just show you, if you took this cell to start with, you would say, well, this plus this is 1, that's odd, so we can colour this one in. If I look here, this plus this is 1, so that's on, so you colour the next line in. So you generate it line at a time. So just like this automaton, it's got time symmetry, because whatever your rule is, you apply the same thing every time step. But it's also got translation symmetry, because the same rule you're applying exactly the same at each different position in the row. And that's a fairly simple rule, and it's generating something sort of slightly unusual looking. A very similar rule generates this, which is kind of cool looking. It might look a bit unnatural, but actually it looks quite a lot like this shell here. So even with a very simple rule, cellular automata can generate quite sort of real-world things, which is promising. Okay, so let's expand and go a bit further. The next step is, well, let's do a two-dimensional version. That was just a single one-dimensional row, so the most famous two-dimensional version is called Conway's Game of Life, and it works a little bit like this. Take the central square, and you look at the 8 surrounding squares, and you count how many of them are on, and you choose whether the central square is on or off based on how many of them are on. Right? You can work out maybe if there are 5 on, you turn it off, and if there are 6 on, you turn it on. So you've got a simple little rule system like that. And it's a very simple rule, and the results are quite impressive. And this is just a simple example. On a 2D grid, I think this is called some sort of gun. They've got names for all these different sort of shapes that they've worked out. But you can see that it's actually generating these little bullets that go flying down this way, and they'll keep on going on forever. So that's the most famous 2D cellular automaton. And one interesting thing about it is that it's Turing complete, which in hand-waving terms means that any computer program in the world ever, it can simulate in this, which I won't go any further into explaining. But it basically can do exactly the same computation that any other computer can do. So
it can be a virtual computing environment, basically?
Yeah, I mean, you can create a floating point unit using these. An entire computer. Here's another. Oh, yeah. I was just going to say that there's some extra symmetries with this two-dimensional version. Because it's just counting the surrounding neighbourhood, you automatically get mirror symmetry. So whatever the state of your neighbours are, if they were mirror reversed, you're still going to get the same result, vertically and horizontally, and also you get 90-degree rotational symmetry in both directions. So if these 3 are on here, then whatever your rule is going to be to turn this on or off, it's going to be the same whether it's those 3 or those 3 or those 3. So it's rotationally symmetric, mirror symmetry, and this is pretty much the same. This is a different one that I found on the internet. Just another example of a two-dimensional cellular automata. 3 different colours, and they represent competing plant species. So you just come up with some simple rules to say, well, if the blue species is next to the yellow species and the green species, then based on which neighbours it is, it might become green or it might become yellow. And whatever it is, the guy that's written this has come up with some rules, and this little time sequence along the bottom shows you that the behaviour is quite complex. This is populations of each of the 3 different colours, and you can see that there's a sort of waving pattern where one plant species will grow and then another species will come in and take over, etc., and you get quite complicated patterns.
What does the red line mean?
I think he did black, he did as a red line, but I didn't really go into the algorithm. So that's kind of where a lot of cellular automata sit. I decided to extend it a bit further with the concept of symmetry to expand into some more symmetries. And the next one that I've been working on is scale symmetry. So imagine the the two-dimensional one we've got already, Conway's Game of Life. And instead of having a two-dimensional grid, we've got a stack of grids now, and each one's at a different resolution. Each one's twice the resolution of the one above it. So these stack of grids just represents how detailed you want to view it. And so, just like Conway's Game of Life, if you look at this red square here, you base the rule on the surrounding 8 squares, but in addition, you base the rule on the squares directly below it, so the high resolution squares, and a few of the squares above it, the low resolution squares. And once you've got all of that data, you just come up with various different rules based on it to choose whether to turn this on or off. And you get results like this. Which to me looks kind of a bit like fire or something. Yeah. A slightly different rule, it doesn't look too different, but it is a little bit different, is this one. It also looks like fire, but there's these sort of rocket jets that kind of fire along. There's a lot of different variations, but here's one that looks a bit sort of more like slime mould on a Petri dish or something.
Looks a bit like Voronoi noise, or Perlin noise.
Well, yeah, they've both got some scale symmetry to them as well, so could be why. So this is different than the normal 2D cellular automata because you can zoom in as much as you like. It's not just a grid. You're not going to get pixelated if you look too closely. You can keep on going. So that's that. Here's a different sort of, well, a few different sort of symmetries you can add. I can't pronounce that, but there's a particular chemical reaction which, if you simulate it, you get sort of, this is a single frame of it being simulated, you get a result like this. And unlike the previous ones, we've extended Boolean to actually using values per pixel. So these are integer values in this case per pixel. That's the frame of what it looks like, and this is a photo of a Petri dish with the same reaction happening on it. So as you can see, there's quite a good correlation. And the formula for it is a bit complicated, but in simplified terms, it looks a bit like this, if you can work out my visualization. If you've got two cells that are close to each other, and this is their value, so each one's got an integer value, so this cell on the left has got a low value, this cell on the right's got a sort of slightly higher value. The cell in the middle, you take the average of the two, and then you add on a bit. So that's your new position of your cell in the middle, if that makes sense. So that rule, because it's just an average plus a fixed amount, is the same wherever you are on the value. So, and it also wraps around. If it gets to the top, it wraps back around. It's basically that. So what we see is we've actually got value symmetry. The same rule applies to whatever your integer value is. Here's a similar kind of thing. This is called a reaction diffusion system. And in this case, they've got two parameters that they can play with. So they've actually plotted them across the two axes. So the amount of reaction goes along this axis, and the amount of diffusion goes up this axis. And so you can see how the shape, the sort of final shape after it's run for a bit, changes based on the two parameters. And it might not look very much like the natural world, but it's quite a good approximation. This sort of patterns here look quite a lot like that fish there, with the spots and the stripes. And this pattern here looks quite a bit like this fish here. And just playing with the same thing, playing with some parameters, you also get interesting results like these. These are both computer simulations, just the same reaction diffusion system, and sort of wildlife that show that they've been trying to match, I guess. But the point is that the formula is simple, it's just being applied, there's a symmetry, so it's being applied the same different positions, whatever the time is, different rotational symmetries, etc. The additional symmetry of all of these type of cellular automata is that you effectively get continuous translation symmetry. So it's not just going to be limited to the individual squares, and you get continuous rotational symmetry. So you get lines like this that don't have to be 45 degrees or whatever, and you get circular values. It depends on the formula, but if you set the formula correctly, then you can get both of these, which is more symmetry than just discrete symmetry. Okay, that's about it. I was just going to finish off with a few links to kind of extensions and different cool projects that people have been doing. Lattice gas cellular automata are actually so realistic that you can model the real equations of gas diffusion with them. These are links, so I can put it up on the website. They included new symmetry, which is time mirror symmetry. So if you play the whole thing backwards, it's the same walls. It's time reversible. So that's an extra symmetry. Someone's come up with quantum cellular automata, which is like pretty crazy, which I think it exhibits phase symmetry. Also crazy, it's quantum Turing complete, that I'm not even going to attempt to tell you what that means. And
Extra geeky, that's what it means.
this is a this is a really cool link. Someone's taken Conway's Game for Life, and they've actually made it have continuous rotational symmetry and continuous translation symmetry. So they've made it, they've kind of made it smooth, and I can't really explain it without looking at the video, but it looks pretty cool. It looks like little cells, like real cells. Pretty cool. No one's done velocity symmetry yet. It's a property of the real world that whatever rules you apply to something, it doesn't matter how fast the thing's going, it's still going to have the same rules apply. No one's done that. I've been trying to do it, but it's a bit hard. So, okay, conclusion. Cellular automata are very symmetric. They're basically symmetric algorithms, and the more symmetry that you put in, the more real they appear to be.
Yeah. Well timed.
15.
You've got 46 seconds to go now.
Oh, for questions? Yeah.
Oh, 5 minutes.
Do more symmetries make the equations simpler or more complex?
The equations don't need to be,
Or the rules, I should say.
the rules don't need to be any more or less. You're just applying the same rule in more situations. So with scale symmetry, you take the same rule, but you're applying it to bigger and bigger scale, which you wouldn't have done without it. Sometimes you need something a bit more complicated because you've got an extra space to work with. Like you've got you've got a bigger set of neighbours in which to make rules. It also makes it harder to search for interesting results when you've got a bigger space of rules.
Are they all, sorry,
No, no,
I was saying they're all local. I mean, they're all local things. Is there any non-locality?
No, it's all local.
No.
Yeah, I mean you can choose how big your neighbourhood needs to be, but it's always local to each cell.
You're still running that in the CPU? You've got to get that in the GPU, man. That's made for it.
Yeah.
Yeah, like your red stuff, like just some of the algorithms you're describing, like one for squirrels, that would just go straight into a shape.
Oh, people have, if you go to, what's it, WebGL playground or whatever, people are writing some cellular automata.
So Tom, do you do recreational pattern making, or you just sit down and spend a few hours making patterns, tweaking the rules?
That's my answer, yes.
I do recreational making bizarre stuff, yeah. That's true.
With the time reversible stuff, does that mean you can just reverse the time step and just procedurally play back, and it'll play back the same way as it'll play forward?
Yeah.
That's pretty cool.
Yeah.
Have you thought of any applications you want to take it? Or
What's
have you thought of any applications that you want to move toward using it for? Or?
I can't think of any. It's a bit abstract.
When you're in games, but then you're like post, or like sort of animated, like sort of 3D packages and like post rendering sort of type things. So animate textures and stuff like that. Maybe?
Yeah, I mean, there are applications, but I've just not time to try and implement something.
Yeah. certainly in the Wiz functions you use a lot in special effects, the cloud,
Exactly.
exactly.
Most of them are not animated sort of things.
Have you looked at, I know you come from that background, have you looked at cellular textures?
No.
Cellular textures is a similar kind of stuff, but actually applied to basically shaders and textures and doing it's one approach to doing like procedural animated textures, that kind of thing. You see what stuff that looks like lava flowing or stuff squeezing. A bit like what's the name of that fluid simulation that everyone uses? Anyone? There's a really common fluid simulation that everyone uses in games, and you get stuff that kind of looks at it like that. It looks like stuff. Well, like you know when you see electron microscope shots of like blood vessels moving through a vein or something, you can do cellular texture stuff that looks a lot like that. And it's the same kind of stuff where it takes simple rules and sort of plays it through. It's nice.
So you can be things like particle type effects sort of take up a bit as well.
Yeah, it's a bit like that. Yeah. And it sort of does relationships and stuff.
You got Matt?
Me going good? Yeah. Rightio. I haven't done PowerPoint slides or anything like that, and what I ended up doing was I got a very fuzzy bunch of ideas in my head of what I was going to say. This is classic Matt for those who don't know me. And what I was going to do is basically, we don't have a massive group, so I'm going to get people to throw questions at me whenever stuff pops up and you go, how does that work, or something like that. I started this off first. So I'll start out with, and also, seriously?
Just replug it on.
He was me saying there's no way it couldn't not work, it's just a thumbstick.
Plug it into a different port then, eh?
Sorry, Tom, I killed your laptop. Let's try that one.
Well, you know how USB sticks are pretty modern.
Hey, there we go. Wrong port apparently. Speed of my system. Okay. Whoa. So just to start with, as I was a bit like Ash was saying with this, I could easily go for like an hour if I said everything I was planning to say, and I was going to try and pitch it on where everyone's kind of knowledge and experience was. So just to start with, can I get a show of hands? Okay, so first of all, just how many people here are actually programmers and do program on a regular basis? Right, so, okay, most of the group, so that's amazing. How many people have done any multi-threading or who do multi-threading on a regular basis? Okay, a few, right, a little bit of stuff. How many people think they have an idea of how cache works? Okay, same people who do multi-threading, interestingly, roughly speaking. And how about, okay, so how many people from the multi-threading group, I guess, know anything about lockless approaches and weight-free approaches to multi-threading as opposed to just using standard primitives? Okay, right.
Getting hazy.
Okay, well, that's, okay, so the people who are probably in the best position to use this stuff are going to be the people who possibly already know it to an extent, which is interesting. So, what I'll do is, this might serve as, I think, a good crash course in cache to start with, because cache, I think, is one of those things which needs to drive the design of game engines going forward. I think a good understanding of cache really dictates how a game engine can be designed, and also is going to be a big influence on the way future stuff is going to work. And my main piece of evidence for that, if I can actually manage to see my files in this next one. Hey, there we go. Here's a little something. Oh, damn! That's what happens when you go from Linux to Windows. That's an extract from the recent PS4 press release.
Just turn on word wrapping, it'll be a bit easier.
Will I do it?
It's I have a WordPad or something else that's on there.
I'll just have WordPad. Tom just okay, just of what that's saying, it's a bit hard to read in that format, this is from the PS4 press release, and the fact that
Everyone sort of was looking a lot at what's going on with the GPU and the CPU. I think the real telling thing in the press release about what's going to be in the PS4 is the fact that they've stuck GDDR5 in this thing, which is extremely high bandwidth memory. And when I saw that, I went, oh my god, this thing is a monster.
Is it high latency too? Sorry? Is it high latency as well?
That I don't know, and I'm very interested to find out, and that actually plays right into a lot of what I started to talk about. And actually, I should start moving through this quicker, I will be here 40 minutes. Basically, GDDR5, incredibly fast, gives you lots of bandwidth, and cache is really key to the way you move stuff around. The whole thing is the trends in computing over time. Everyone should know by now that mobile phones are already up to 4 cores. It is common for brand new phones you buy. PlayStation 4 is going to be 8 cores. You can pretty much guarantee that the Xbox, the new Xbox, will be 8 cores as well. And basically, memory speeds are not going up as fast on the CPU and GPU as the number of cores and the amount of speed the chip is going. So over time, basically, the amount of memory you can pull in from your pools of memory that are further away is reducing relative to the amount you can do with that. So it means that over time, the way you need to design engines needs to be based around only touching memory once, if you possibly can, and doing as much with it as possible before you write it back. Now that's a whole other talk I can do that might even be a series of stuff that goes into that design. And what I wanted to start with today, though, is the multi-threading aspect of that and the communication between threads, because we're now getting up to the point of 8 cores. And moving forward, we're going to move to the point where if you take a GPU already and they're getting more general purpose and doing something like CUDA, you might have 192 cores working on something. If you use your standard multi-threading approach of using, for just a bit of a review, the primitives for multi-threading that people would be used to is mutexes, conditions, read-write blocks, those kind of things. Semaphores. They're all locking approaches to multi-threading. What that means is you have a piece of memory and you're using, say, a mutex, for instance, to guard that piece of memory. You say, I exclusively have access for this, I'm going to use that for a while, then I'm going to release it, and then other people can use it. And what you end up with is, what you can end up with in that situation is what's called contention, where you have multiple things all trying to use the same piece of memory at the same time. If you go to 192 cores and you have contention on a piece of memory, your performance will just go through the floor. So we're in this strange window of time at the moment where we've moved up from 1 core and we're up in this sort of this low numbers where we're like 2, 4, getting up towards 8 where it's starting to matter. That number's never going to go back down realistically. We're going to end up with more cores. So what those 2 trends tell us about computing is that generally speaking, cache coherence is really important, and you want to minimize contention as much as possible. Now, how am I doing for time, actually?
Sure. Just under 10 minutes.
Good. Okay. Okay, so for people who aren't familiar with cache and understand what the concept is, basically cache is a way to sort of have a temporary store of what's in your RAM that you can access much more quickly than you can in main memory, because the same stuff I was sort of talking about, you sort of start treating things as being a certain distance from your core processor. The classic thing in this kind of diagram as well, at the very top you would usually have network as well, which is, you know, if you're pulling data over the network, that's going to be slower again than pulling stuff from the local disk. So you sort of have this hierarchy of how quick it is to sort of hit certain parts. So it's actually relatively slow to go to main memory. People used to do it sort of back in the days of 286, but these days, if you're using memory regularly, you're going to be moving in and out of cache, because that's basically way faster.
Just a question.
Yep.
As I understand it, NVIDIA is moving their memory onto the GPU die. Where does that sit? Is that effectively cache then?
That's
or is
that's effectively cache. Without, again, not wanting to go on for hours here. The idea is basically when you start moving stuff onto the chip, it gets faster, and that's sort of, you get these. Actually, well, this will lead straight into, if I can get to another picture I was about to bring up. This is the way that sort of thing starts to move. Even when you start moving the memory onto the chip, it gets way faster, which is the way cache works. The thing about cache is, though, once you're on chip, it's and it's that fast, it also becomes about how far away on the chip is it. Because everything with computing is everything to break up the die and have chips further away from each other. So you end up with these little pools of RAM that are sort of nearby to the chip so that they can access them quickly. And you end up with, one piece of memory that's really close to your core, and then your L2 is a bit further away, and then usually there'd actually be like an L3 here that's kind of shared between all four, if that makes sense. And then you go out your system bus and your main memory. The thing is, you're never going to end up with, we're going up to, 16 gigabytes sometimes on graphics cards. You're never going to cram 16 gigabytes. Well, look, no, Moore's law works. You're going to get 16 gigabytes on your GPU, but by the time that happens, you're going to have a terabyte of RAM sitting next to it. It's the whole point of that sort of pyramid drawing I was showing before is that it has to do with sort of the decreasing margins. And stuff is always kind of going to shuffle down that thing. So it's the same as hard drive sizes get bigger and bigger. As RAM moves on chip, it's just becoming more like cache. You're going to get more and more of it, but it's always going to be, there's always going to be more RAM and more storage, whether it be disk storage when you get to like virtual memory where you've got swap space and stuff going on out to disk. You're always going to be moving from the thin edge of the wedge to the top end of the wedge. So that's why it's just because you hear that it's moving on a chip doesn't mean you can forget about it, because the pyramid always stays the same. That's the thing, it's constant. And if anything, the pyramid's getting tighter because, as I mentioned with those trend lines, the CPUs are getting faster, quicker than the storage is growing. Okay, so the other thing to note is this is basically coming into that distance thing I was talking about, where you want to hit L1 cache whenever you can, is the idea. Now, L2 cache is better, L3 is better than main RAM and so on. Now, the thing that to sort of understand about this stuff with cache as well is once you start hitting multi-threading, you can sort of see how there's a big difference between getting something from main memory and getting it from your cache. And if you change a piece of memory that's like, say, that you then want to be read by another thread, if that thread is running over on core 3, for instance, this core, in order to communicate with core 3, is kind of got to do it via the L3 cache that we don't really have shown here, if that makes sense. So, understanding how many, show of hands, who understands what a cache line is? Okay. How am I doing for time again?
5 minutes.
5 minutes. Yeah, as I say, I could easily go for 40 minutes on this, I think. Okay, so everyone sort of understands the structure of memory. This is sort of the way I think people who've started out in programming but hadn't got kind of to this level or gotten something like console programming where you get closer to the hardware. This is the point where when you start to understand this stuff, it sort of starts to shift your whole perspective on the way, your mental model of the computer, if that makes sense when you're programming. You often start out just thinking of memory as the way the addressing usually works, where basically you start at memory location 0 and then you go to however much RAM you've got. And it's just this big long line. And then as you get more complex, you realise that, okay, no, you pretty much need to do, when you hit like a quad, for instance, you don't want to have misaligned quads, so you always want them to be on your nice 4-byte boundaries. And often there are chips that will only even let you load a 32-bit value on line boundaries. Then often people get to the point where you start running vector stuff, and you discover that you have a vector for SSE instructions or Neon instructions on ARM, and you deal with 128-bit 16-byte values where you can basically do 4 operations at the same time. You've got single instruction, multiple data. The next step up from that then is what you kind of call the cache line, because these caches don't all just deal byte by byte, because that wouldn't be terribly efficient. What they deal with instead is a cache line. So on these days, you're usually dealing with either a 32-byte or a 64-byte, if you're on a 64-bit architecture, size of a cache line. Now what that means is when you go to access a particular byte, even if you just say grabbing a Boolean value that's 1 byte, and this core asks for it, it doesn't just grab that 1 byte from main memory. What it does is it says, I want that. It grabs the whole cache line, if that makes sense. So it'll grab the whole 32 bytes or 64 bytes and pull all of that all the way up to here. Now, if somebody else Now that actually comes into an interesting point, because if you think about the fact that it's now got control of that cache line, so 64 bytes it could be. If you then go in another thread that's say running down on core 3, and you change the last byte in that 64 bytes, what you get is called, you've got contention going on that cache line. So what happens in that case, you have what's called cache coherence, which is all these caches talk to each other. When I modify the first byte, okay, it says, okay, that's dirty, if that makes sense. That cache line is told to be dirty on all of these. So if this guy then goes to read the last byte on that cache line, it will have to do is, this cache has to evict that cache line back up to L3, and then it'll get pulled up over here, if that makes sense. As you can imagine, that's a bit inefficient. So you want to avoid that when at all possible. So you can see how that goes into that whole engine design stuff I'm talking about. Generally speaking, when you're doing multi-threaded programming, you want to keep your different cores all touching separate cache lines. General rule of thumb to work with that is if it's within 64 bytes of it, and that works on align boundaries, if that makes sense, that everyone understands what I mean when I'm talking about the line to the 64 bytes. So basically, if you have separate threads, you want them to be working in totally different cache lines, and yeah, there's no way I'm going to get into all the stuff I wanted to hit. Like I say, I could go to 40 minutes on this. And the other thing is, if you're doing multi-threaded communication where you're sending data from one thread to another, you want to ideally not have, for instance, these two cores touching that piece of data, so that your communication can kind of go through this path, if that makes sense, rather than going through this path over here. Okay, I'll sort of fly through the rest of the stuff if I can, and you guys can tell me if, I'll see how many people's heads are swimming, and how many people might want me to turn this into, okay, so I did have a diagram showing, this is cache contention, false sharing is what it was called. So if this guy's working on the first byte of the cache line, this guy's working on the last byte of the cache line, you end up with contention, even though they're not actually touching the same byte, if that makes sense. So you've got all this extra traffic that's meaningless. That's called false sharing. Sorry, I forgot to have a picture for that one. Okay, so when you get to multi-threaded communication, now people are probably very used to using things like mutexes and that kind of thing. One of the main things I sort of wanted to hit today was that 15 minutes?
Yeah.
Okay.
Give another 5 minutes. Just wrap it up and get some questions.
Yeah. Okay, so this is sort of get the crux I wanted to cover. I've sort of given you the background now. The main thing I wanted to sort of try and teach people today is that when you're dealing with something like a mutex, what you're really doing is, it's kind of like working with the standard C sort algorithms and using them through your whole programming career without ever really understanding how the sort algorithm actually works inside. You sort of get to a different level sort of once you understand what's actually going on under there, if that makes sense. What's the actual hardware do? So now that you guys sort of get the gist of how that case structure works, that sort of will run a bit with this. The thing about, if you get to lockless programming, and you get to basically what can the hardware do to do communication between threads, it basically comes down to two main bits. Now, really quickly, just talking about that cache, whenever you do reads or writes to a piece of memory, you can never ever trust what order that change is going to hit main memory. And that's for a bunch of reasons. The first one is, as most people are probably aware, your compiler reorders everything you do to make it faster. So that's the first one, is your compiler is going to reorder it. These days, a lot of chips like x86s, which are in lots of stuff, and PowerPCs are even worse in the way this sort of stuff works. The CPU actually reorders the way it does, the order it does its operations in. And with what you just saw about the cache, and the way that structure works, that might sort of explain that, because you can sort of imagine, if you go for a piece of memory, and you get a cache miss in L1, it's got a long way to go to get the main RAM potentially before it can pull that bit of memory into working. So what CPUs do instead, they sort of look ahead a couple of instructions and they go, oh hang on, there's an instruction that doesn't depend on that instruction, and I've already got the memory I need for that in L1. I'm going to do that now while I'm waiting for that other bit of memory to go happen, to go do a fetch from main RAM. So CPUs actually reorder the order they do stuff in. The other thing is, once you're writing back to the chip, depending on how frequently you're writing to that cache line, or whether you've written to something and then you've left it alone, you might change the order about when the controllers decide to evict up to higher levels of cache and then finally push it up to main RAM, if that makes sense. So there's all these different levels and layers of stuff going on that reorder stuff. And you might sort of think about, if you start to think about the way multi-threading works, the naive approach when programs first come in is, oh, it's okay, I can just make a volatile variable, and I can just say, oh, okay, and when I'm done here, I can just put a 1 in that volatile variable, and the other thread will know that it can move on and do stuff with it. So now that you guys sort of understand a bit the way all those different elements interact, you can see why, yeah, that never ever works. That's the reason you have to use things like mutexes to control your stuff. But when you get down to the lower level, there are basically two things that get used to do the control of all this stuff, to do thread control. That's atomic operations and memory barriers. And these are the two things I want everyone to, if you're going to do this kind of stuff in multi-thread, go away and learn about if you don't know about them already. An atomic operation, it's whatever your fundamental primitive size is on a chip. So if you're working on a 32-bit chip, it's usually a 32-bit value. If you're working on a 64-bit chip, it's often a 64-bit value. What that means is when you make a change, if we go, actually I should go back to that cache diagram. So if you write to a 32-bit value, you can be basically assured that another chip is not going to see the low 2 bytes, if that makes sense, without seeing the high 2 bytes. So that's what you can call an atomic read or write. If you read or write to a 32-bit value, you're never going to get like half of that read or half of that write.
Word tearing.
Sorry?
We call it word tearing.
Word tearing. And beyond that, there's actually a couple of instructions that CPUs will let you do. That basically, if you think about, you had sort of the way that stuff works, where you can sort of operate in your registers, and then you sort of write back to cache. This isn't the way they actually work, just to be clear, but the atomic operations are usually compare and exchange, compare, increment, decrement, and you'll find these as, actually I think there's probably something here. Anyway, so you can do these operations that are atomic, and the other chip will basically, so now, compare and exchange is the most important one for multi-threading. What that basically says is, I think that there's a certain value in that atomic value, that's my other 5 minutes, is it? Yep. I think there's a certain value in that, I'll try and wrap it up really quickly. There's a certain value in that atomic value in memory. And you basically say, if that turns out to be what's there, then stick this value in there instead. And what happens is, so basically just say, I think there's a 0 in that 32-bit value. If there is a 0, stick a 1 in there, and then it also comes back and tells you what was in it. And if it turns out it was 0, you know there's now 1 in there. And if it turns out there was a 2 in there, you go, oh, hang on, that means there's a 2 in there. So what it means is, it means maybe change that value in cache, if that makes sense. And it won't change it if your expectation doesn't match up. That's a really important part of being able to communicate between threads. And the other one is, I mentioned how you can never trust that order. There's actually what's called a memory barrier. And a memory barrier basically says, I don't want any reads or writes to pass each other through this section. So what you can do is you can say, write A, write B, write C, stick a barrier in, and then write D, E, and F. Now, you can't ever trust what order A, B, and C will be seen in, or what order D, E, and F will be seen in. But what you can do is, so if you're on core 0 and you write A, B, C, barrier, D, E, F, then on core 4, you say, right, check value D, then do a memory barrier. You can be guaranteed that if D has been written to, that A, B, and C will already be there because of the barrier. Do people get what I'm saying, or does that make sense? Yep, okay. So that's basically, and that not only tells the compiler not to reorder your instructions around that when you use a barrier instruction, it also tells the chip not to reorder around it. So these two elements, atomic operations and barriers, are basically everything that you can use to communicate between chips. Do people mind if I go to 25 minutes, or I can cut it off now and say this can be the next talk if you want.
I think Miles, are you still going to do a talk?
Yeah.
So, you've got a few minutes if Miles. Was there anyone else who's going to do a talk? After Miles? No? Cool. Yeah, get done it.
Okay. I'm moving a bit fast. Like I said, I probably could have done this in 40 minutes and allowed for more questions and made it a bit simpler. What this is from the Android open source project. It says normal lock, but this is basically a couple of levels deep. This is a mutex lock in Bionic. Now, the reason I'm using the one from Bionic is the Android standard C library. The reason I'm using this is because mutexes in most operating systems are actually designed for synchronizing between processes, which means you're dealing with a whole other kettle of fish we're not getting into now, which is memory that's shared between processes as opposed to stuff you're just doing within your one process with multiple threads. Bionic is designed to be really, really fast, so what they did is they created a cut-down version, which just does the simple version that's just for communicating between threads. So I want to run you through the way a mutex lock and unlock works and show you that it's just made up of these simple CPU primitives. So the lock basically says, do a compare and exchange. And basically what you do is, your mutex value is usually 0 when no one's got the lock. This basically says, if the mutex is 0, stick a 1 in there. And then you check your result. If the result comes back and says there was a 0 in there, then you know that you've now stuck a 1 in there. Therefore, I have the lock, if that makes sense. And if it comes, and yay, I own it, and then the next thing you do, damn it. Yeah, I did. So you go, and if you have that, you go, hey presto, I've got the lock. You do a memory barrier. That's very important to realize what's going on. You go, comparing, so one atomic, one memory barrier, and hey presto, I've got the lock, because you know that value being written, and you know anything you did before that point is going to be seen in memory before anything you do after this point, because you have a memory barrier. If it turns out you get something back other than 0, that means somebody else had the lock and you start to go into a wait. This is the stuff that's not going to work when you get to 192 cores, like I was talking about. Then, when you go to unlock it, you sort of do the same thing in reverse. Another memory barrier, then you do an atomic decrement. So basically it's dropping you back down into saying, okay, put it back to 0 now because I'm done with it. So what this should show you is that to do, say, a mutex lock on a piece of memory, you're doing an atomic value, then a barrier, then do some stuff, then another barrier, then another atomic operation. Now the thing is that these memory barriers, and this is much more expensive than a standard operation to do these atomic operations, and these are really expensive. This is why people talk about multi-threaded stuff being expensive, and that's why you don't want to go doing a mutex lock and unlock inside a tight loop or something like that. The solution is that you can use this stuff instead, and you can go away and instead you can do what's called lockless programming, which is basically a way where once you understand that these primitives are made up of these smaller elements, you can change your approach to programming, and instead you can get away often with just going, write a bunch of stuff, do a memory barrier, write another value, move on, because I've sent something to another thread. And I've way gone over my time, so I might leave that for another talk. So what I've done now is I've given the background, and next time, in the other little bit that would take me up to 40 minutes, I can possibly take people through and explain a bit how that lockless wait-free stuff works. But hopefully I've given people a background, and if people are interested in it, they can let me know, and I can go through and take you through what these other approaches are that will work better on GPU computing, and as you start going beyond, to 8 cores and beyond, so you can start communicating directly through these CPUs without having to do the locks that are actually fairly expensive operations.
Yeah, I'd be up for you doing a bigger talk. I'd really like to hear more of that.
Cool.
Yeah, same.
Yeah. Good stuff. So just check that. So how many people have sort of done that stuff before and went, yeah, I've heard of that before, and I know I've done lock-free, or I understood how mutex works.
Mutex can do.
Cool. Okay. So I'm in a territory people use. Cool. Okay. I'll let somebody else go on.
I think it would help next time as well to overview the basics. It's been a while since I've delved into some of this stuff.
See, the whole thing was I thought this could easily be a whole session talk, and I just haven't had time to put something up together. So I've got 50 minutes.
That was a good taster session.
I ran through it pretty fast.
15 minutes isn't very long.
No, it's not. It's not.
Like, it might be 5, maybe.
Yeah, right. So I actually wondered whether, like, if everyone had a go on, yeah, we get how all that, the standard bits work. I thought, I might just end up doing the second half, or I thought, if no one got the first bit, I thought, maybe I'd just do the first half.
Oh, yeah.
So it's kind of like we've got different levels, so I sort of didn't quite know where to pitch it.
You might want to use someone else's laptop as well, like press escape this time.
Oh,
Yeah. Hey, what's that about the warning button? Oh. Using my phone as a USB. Wait, hang on, I think it worked. Yes. Okay, that was lucky. Or was it? Shit.
That was pretty temperamental.
Yeah, yeah.
Yeah. Stick it forward. You might want to try someone else's laptop as well.
Does anyone else have a Windows laptop?
Yep.
Try it a few times first.
Had to be different.
It's a pretty old computer now.
It's a nice big screen.
Yeah.
Probably worth it. Yeah, so I was thinking of doing a YouTube video. So basically what I want to talk about was a project I've been working on over the last few months. It's basically just a mess around project where I concept a game and then look at a bunch of areas that I want to work on and learn about, and then I put those into the game. And I've been into a YouTube video, but I haven't yet, so I kind of wish I had now.
How do you need the good GPU for this?
No, it should be right. Cool. Nice. This is promising. Doesn't look promising.
Is that it? Is that drive, dude?
Yeah, what?
E drive?
No, that's not mine.
Oh, that's an old thing.
Yeah.
So F drive is not. One thing you have to do, I found on Android, is you have to actually, there's a button
Put it
you
into
press to actually.
to turn it on.
Yeah.
And I just turn it on.
Oh,
I got an Android. Okay. So while I'm messing around with this, I'll give you a quick run through. It's basically it's written in C++ using Ogre. There's a couple of other libraries I'm putting in. Nothing really fancy. As I said, it's just a project I'm looking to learn about it, learn about various technology and libraries and stuff. Wow, that was a PowerPoint. Oh well, let's jump into the game. So the game is basically a 5-second pitch is that it's Minecraft in space. So the concept is that you take a realistic kind of construction and put it in a space setting, and then players it's sort of sandbox, so players are free to do what they want and build what they want, and then maybe at the end they'll have a ship which they can go and explore the galaxy, or they'll have laser cannons and stuff if they can fire at pirate ships. So this is basically it. So you're just floating around in space. There's really, really shitty texture. The skybox is basically just an inverted sphere which I put a texture on. But I'm looking at some cool options for that in the future. So at the moment, all that I've got implemented is basically just construction, but the core of it is working. So the world is divided up into a 3D grid, and each of these, so you can see it's obviously a grid base there. So the basic construction is you put a girder on each grid. So here I've got the build overlay set up. There's actually a cool shader I've got which will highlight that and make it glow, but it's not working for whatever reason. But I can build out from any of the existing constructions, similar to the way Minecraft does it. So if I can remember the controls, right? Yeah, there we go. So I'm building out sort of a wall thing here. And I can go bam, bam, do like a tower thing there. And that's kind of cool. And that's how you build the basic construction. Then you can build stuff onto those girders. So if I can remember the controls, 1, 2, 3. Yeah, there we go. So I can now put plating onto the side, any side of those girders. And so now you've got basically a wall. So the idea behind this is that you build a ship by doing that. You've got the girders here, and this is like a maintenance corridor going through here. And then just on the other side, there's this cool tunnel kind of thing. And so eventually there's going to be things like you'll be able to put doors onto specific spaces. So there could be a door here, and then you just open it and walk through like that. There's one of the cool things which I can show off, and that's basically anti-gravity. So the way I'm implementing the world is that eventually you'll be able to build things onto each specific girder. So this wall here, in the same way that I was able to mount plating onto each different face of the girder, I'd be able to mount certain machinery onto that plating. So for example, I'd be able to put a light fixture there or something which would light up the tunnel.